So let me start by sharing my screen. And let us do a quick recap because we have done this, I think, 2 weeks back. So can you all see my screen now? Can you see the lecture notes?
Yes, sir.
Okay. So, so far what we have discussed is considering a stochastic differential equation, which is a differential equation with stochastic coefficients, and why we need that. There are situations, natural situations, where such a stochastic differential equation would be relevant. And then we have tried to understand what kind of disturbance term would be consistent with this formulation. And that formulation leads us to a slightly peculiar Brownian motion dependent formulation, which has infinite variation. This we have discussed last time. But if we ignore that infinite variation problem, we can at least write the stochastic differential equation formally in terms of differences and then taking limit. So we start by looking at the difference equation, and then we take the limit, and our candidate for the error term is the usual Brownian motion difference or Brownian motion differential. So that's where we stopped last time. In general, we were looking at a linear stochastic differential equation of the form dx equal to ax dt plus db. And db is the noise term. And we have also discussed that this is the only candidate with continuous paths. So it is not only one particular choice, this is the only choice if I am insisting on continuous paths. And the rate of variance of this dB is of the order of dt. So the variance of dB can be notionally thought of as equivalent to dt. All right. So with that, our job would be to give a meaning to this particular integration process, because this integration process will help us to solve the differential equation. So we are looking at this formal expression at the top here, dx. So if I want to find the x process, the distribution of the process x, I will have to integrate. And that integration formally will give me two parts. One is a ds integral, which is the usual integral, Riemann type integral that we already know. But there is a second integral which we have to understand. This integral is a dv integral. So this integral is not an usual integral in our usual Riemann sense, but this is important in the sense that if we can give a meaning to this, and if we can essentially find the distribution of this integral, because again this integral will be a random variable. So if we can find the distribution of this integral, then we do know the distribution of xt. So that's what we set out to do. And like all integration theory, we start with simple functions on which we will define the integral, and then we will try to expand that class of functions to encompass all the relevant ones. Of course, we will not be able to consider all possible functions. That will be too much to ask. We will try to get to a point where we can cover a reasonably large class of functions on which we can define this stochastic integral. So is this clear so far? Is the context clear?
Yes, sir.
Yeah. Okay. Thank you. So then our first job is to start with a simple class of functions to define the integral. And if you remember your undergraduate days, we started out defining integrals with rectangles. So our initial attempt at defining integrals was involving step functions. Using step functions, we have rectangular kind of graphs, And on rectangular graphs, we can find the area very easily. And as you know, that area is the integral. And then we use the concept of limit and extend our class of functions. That's what we did in our Riemann integration class. We will do a similar exercise here, keeping in mind that we are handling a somewhat more complicated object because we are considering a stochastic integral. But the starting point would be similar. All right. So let us think of a range from capital S to capital T, where capital S is non-negative. So it is like a finite interval on the real line, positive part of the real line. And suppose my function f is given. So function f is a function of two arguments, time as well as the omega, because it's also a random variable. And I want to define this object integral of f dvs. So we start with step functions, as I mentioned. How do I define my step function now? I have to keep in mind that my step function will not only depend on t, so it will be a step function over time. Time is the x-axis, but it will also be explicitly dependent on omega. So I define ft omega for each omega as a step function of this type, that in the interval j to j plus 1, where we are cutting the whole s to t interval into 2 to the power n pieces. So I am not going into details here because this should be familiar to you from your earlier Riemann integration theory. So basically I am cutting the interval into 2 to the power n pieces, and within each piece I consider the function to be a constant. Well, when I say constant, I mean to say that given omega, it's a constant. So it still remains a function of omega, but it is not varying with t within that small piece. So the small pieces are like j by 2 to the power n to j plus 1 by 2 to the power n, indicator of this interval on the t line, and the value of the function will be given by ej omega on piece j. And I sum over all the pieces. So in effect, I am looking at a step function for ft omega. Is that clear? Is this formulation clear? Because this is very similar to what we did earlier. The only difference is I have to insert omega to take care of the stochastic nature. Is it okay?
Yes, sir.
Okay, thank you. All right. So if I have such a function f, and I am looking at this integral f dvs, then my integral will also look like this. So when I am considering the interval from capital S to capital T of this f dv, then it will be essentially summation over j, all these values at each interval j, ej omega, given omega, and the increment in dB. And the increment in dB will be given by btj plus 1 omega minus btj omega. Okay? Because within each piece, f is not changing. F is fixed at ej omega. So only thing that is changing is b. So all I need to consider is the right endpoint value minus the left endpoint value. That will give me the increment dB for that interval. So a summation over all the pieces will give me the total integral from capital S to capital T. And obviously my choice is ej omega will be the function value f at some tj given omega. Now, a little bit of history. I am choosing the function value at the left endpoint. Tj is the left endpoint. In Riemann integral, we also did same thing, but we also knew that even if I took some other value within that interval, the final result will not change. If you recall, this discussion is there explicitly in any analysis textbook, that choosing the left endpoint is just a matter of convention. It doesn't matter in the final result if we choose the right endpoint or some point in the middle. So for Riemann integral, if I choose a T star instead of Tj, where T star is somewhere in Tj and Tj plus 1, it will not matter in the final result. The integration theory will give me exactly the same integral values. The first surprise, probably not a surprise, but for the first significant difference between a stochastic integral and a Riemann integral is that now this choice makes a difference to the final result. For a stochastic differential equation or for a stochastic integral, if I make a different choice of T star, I will get different answers in the integral. Why do you think this should happen? Can any of you tell me why this should happen? That my choice of T star will matter in the final result? Anyone? So let me repeat my question. In Riemann integral, the choice of the function value within the interval does not change the result. By convention, we usually take the left endpoint, but even if we took any other point in that interval, the final integral results would remain the same. I now claim that for a stochastic integral, this choice makes a difference in the final result. Why do you think it should be so? Anyone would like to guess? So there is no response. All right. So if you are not going to respond, then let me continue with my explanation why this should be so and so on.
Sir,
So
is T star dependent on omega?
T star, you mean the choice is dependent on omega?
Yes.
No. No. All I am saying is that I can choose any arbitrary T star within that interval. For a Riemann integral, I could have done it anywhere and the result would have been the same. But now I claim the result will differ depending on my choice. You see, I cannot make T star dependent on omega because then the distributional properties will not hold true. You understand? Because finally we are interested in the probability distribution of the results. So if my choice of T becomes dependent on omega, then that choice itself becomes a random variable. Then it becomes very, very complicated. Do you understand what I am talking about, Nobonil?
Yes, sir.
So that the choice here is critical. The choice not only cannot depend on omega, because then the T point will also become uncertain, which would be too much to handle. Also, my claim, which I am going to defend now, is even if it is independent of omega, the choice of T star makes a difference in the result, in the final integral result. So once again, do you want to give it a try? So I'll just open this picture here. And now can you try and explain why this result should differ? This picture may help or may not help, I don't know. I just wanted to draw something to represent my intuition. So this is the usual rectangle setup. And this is Tj and this is Tj plus 1, the left and right endpoints. And what I am now drawing here is a graph of the function. And because the function is not a deterministic function, I am sort of trying to represent it using confidence intervals. In a very intuitive way, I represent my function by confidence intervals. And the point I'm trying to make is the following, that the uncertainty. So when I am standing at the left endpoint, if I choose the function value at the left endpoint, then there is one kind of uncertainty involved. I know the current distribution. I know the whole history. But if I choose the right endpoint, then I don't yet know the whole history. The right endpoint. Can you make yourself mute? Ronak, can you mute yourself? Okay, so my logic is based on this picture, that when I am standing at the left endpoint at the start of the time interval, if I take the function value at that point, then I already have the full history, full historical information at the left endpoint. But if I consider the right endpoint value or any other value in the middle, then the history is not yet fully known. So the uncertainty involved with that particular value is different depending on the choice of the T star point that I make. Is this clear? Is the point I'm trying to make sense? Is the point making sense, or should I repeat once more? So we were of course. So we were trying to define integral through step functions as usual. In Riemann integration, the value, rather the time point at which I calculate my step function value does not matter. Within the interval, say Tj to Tj plus 1, whether I choose the left end point at Tj and take the value of the function there, or I take the right end point Tj plus 1 and consider the value of the function at that point, does not matter to the integral. The final integral will remain the same. In case of a stochastic integral, I claim that this difference does, this choices does make a difference. Why? Because when I am standing at the left end point at the start of the time interval, because you see for the rest of the time interval, I'm going to consider the function to be constant, but it is not actually a constant. There is some changes which I'm ignoring. But not only there is a change, there is also variability that is involved here, because the function is actually a stochastic function. So if I am standing at the left hand point Tj and I choose my T star as equal to Tj as the left hand point itself, then I already know the full history up to the point Tj where I am measuring the function value. But standing at the start of the interval, if I choose T star as Tj plus 1 at the end of the time interval, the right end point, then I do not yet know the whole history. So whatever is going to happen between Tj and Tj plus 1 is as yet unknown to me. So the uncertainty involved in the function value is different. If ft star is ftj plus 1, the uncertainty involved is different than if it were f at tj. And this is how I represent this intuition pictorially, that when I am standing at Tj at the left endpoint, the uncertainty involved is something like this. But if I were considering the right endpoint value, then the uncertainty will be more, because the whole history in between Tj and Tj plus 1 is as yet unknown. So if you are thinking of formal language, then this is basically the FT adaptedness. So the left end point here is actually adapted to this point. So the history is known up to this point. But if I am choosing the function value at the right end point, then this value here is not FTJ adapted. So I do not know the whole history. So the uncertainty involved is different. Does it make sense now? Can you just
Yes, sir.
think about it a little bit and tell me whether this is making sense, because this is a very important point, and if this point is clear, then the rest is more mechanical. The rest is just constructing an integral, which you have seen before. The real non-trivial difference is right here. Is this okay?
Yes, sir.
Yes, sir.
So if this point is clear, then what I can say now is that, you see, if I make a different choice, I will get a different result in the integral, which means the integration theory or the integration formulae that I am going to develop, they will all be dependent on which point in the time interval I choose. So what is my choice of T star? Now, the left end point choice happens to be the most popular choice, really, which is called the Ito integral theory. So the Ito's theory, Ito developed the integral theory, making the left end point choice, which is actually the easiest. This is easiest because, you see, if you look at the summation here, if I choose the function value at the left end point, then this increment is entirely independent of the function value here. So this is a product. So when I am going to evaluate the integral, that would mean I am going to evaluate the probability distribution of the integral, or I am going to evaluate the probability distribution of this summation. Now in each summation, in the summation, each term here is a product of two terms. If I choose Ej to be the left end point value, Ftj, then the function value here will be independent of the Brownian motion increment, because the Brownian motion increment starts from that left end point and goes further to the right. And as you all know, that these are independent. So the summation process will be relatively simpler if I make the left end point choice. If instead I choose the right end point choice or some other choice in the middle of this interval, Tj to Tj plus 1, then there will be some dependence, because there will be some overlap in the uncertainty. So Ft star will involve a part of the same uncertainty that is involved in the increment of the Brownian motion. Am I making sense?
Yes, sir.
The uncertainty is evolving over time. So if there is an overlap in the time interval, that means there is dependence or correlation in the uncertainty. And that correlation will definitely make my calculations more complicated. I am not saying they cannot be done. They can be done, but they will be slightly more complicated. And that's why Ito's choice happens to be the most popular choice. But there is also another choice which happens to be popular, not as popular as Ito's, but somewhere close, which is the midpoint choice. So the midpoint choice led to another integration theory, and this is due to Stratonovich. So here is a typo, so this will be Stratonovich. So there is a V, N-O-V-I-C-H. So Stratonovich's choice was the midpoint, which means there is some common uncertainty between the dB term and the function term. But the corresponding integral theory can be developed. we will stick to the ethos choice because ethos choice happens to be the simplest, and in financial applications that is typically the one that is used by almost everybody. So for us, the stochastic integral will be defined through step functions, which will be of this form: summation over ftj omega, and then the increment in b, so btj plus 1 minus btj. So the integral here will be same as summation of f db, where f will be evaluated at the left end point. And then of course we'll take limit by making the interval, the pieces smaller and smaller, which means we will take this n to infinity. Because n controls how many slices I make, so I will take n to infinity, and the limit of this sum will give me the Ito integral. Okay, so is this okay so far? Because I am just trying to replicate the Riemann integral idea with the added complication of uncertainty. So my choice of T star makes a difference, but I am making the left endpoint choice. Okay, so with that,
Sir,
yes.
sir, I have a little confusion in this. So in Riemann integral, what we do is define it for the lower sum and the upper sum in each interval by taking the infimum and supremum of the function. And then if the limits in both cases are equal, then we say that the function is integrable and define it as that limit. But here you are saying that we are not going into that complication, we are just taking the left hand point. Well, so if that
Because
is the
as
case,
I already told you, if you go through with the usual Riemann principle of the sandwiching argument, it will not work here, because the right endpoint and left endpoint will give you non-trivially different results.
yeah, because if, for example, and not only that, because suppose you take that function, the characteristic of rationals. Okay, so in that case, that Riemann integral it says that that function is not integrable. I understand that because there one side is 0, the other side is 1. But if you take any such choice of t like this, then the value of that function is always 0. Value of the integral is always 0 because whatever you are choosing is a rational point. So, but this integral should not be 0. I mean, that defies our general intuition.
No, that will not be 0. See, otherwise this is exactly in the Riemann sense, because I am not going to play around with the length of the intervals. You see, when you move from Riemann to Stieltjes integral, what you basically do is make the dt variable, the delta t parts variable. And that is where you are basically going to be allowed to take out the rationals, and then you go into a sort of measure zero kind of idea, which is formalized in the Lebesgue integration. I am not going that route. As I said, I think Navonil asked this. I think Navonil asked a similar question. May not have thought about this angle, but it relates that my choice of t is not dependent on omega. So my choice of t I make completely autonomously.
Sir, but then how is the concept of integrability defined here?
Right. I mean,
Yeah,
Riemann
so
I mean,
integral allows.
I can say
that I
a
will
function is
formalize. Yeah.
Riemann
That I will have to
integrable or
formalize.
Lebesgue,
Okay,
but what is Ito
hold on.
integral?
That I have to formalize. I have not yet completely described the functions I am going to allow. So just hold on for a little bit. So to complete my theory, I have to specify what are the restrictions I'm going to put on my functions, so that the functions behave in the way that you are expected, you expect them to behave. As in that Riemann sense that you can do the sandwiching, etc., etc. All right. So just hold on to your question for maybe 5-10 minutes. Let me define the class of functions I am going to allow, and then we can get back to answering that question. Okay. So step 1 is we have started out with the rectangles, the step functions with a particular choice of endpoint, which we call the Ito integral. And then we take the limiting process, etc., which hopefully will give us the consistent theory. Now, before I move ahead, as you rightly ask, I have to clarify what kind of functions or what kind of properties I want to impose on my functions so that my integration theory is really consistent. So if I make the Ito choice, you see there is a very important property that I get, that my choice of f, the ft star omega, that becomes ft adapted. Because when I am starting at the beginning of an interval at the left hand point at tj, and I make that point as my choice of t star, then the function value there is ft adapted. So I know all the historical information. And this is the key. This is the key in what we are going to define going ahead. So to understand that, let me first look at this result, which we are not going to prove, but just try to understand what this means for us in terms of defining the integral. Now, the result is the following. So this function af is ft adapted. This is equivalent to saying that the function can be written as pointwise limit of sum of functions of this type. So it's a slightly complicated sentence. So what I am looking at is, I am looking at products of this type where the points are evaluated at t1, t2, tk. So I evaluate b at t1, t2, tk, and I take some function g1, g2, gk, bounded continuous functions of them. So these functions are bounded continuous. So I take a product of this type and I then take a sum of such products. And I can take the pointwise limit of sum. So these are the type of functions which are all allowed now, because this result tells me that all such functions will be ft adapted. So this is a slightly complicated way of saying it, but in essence, what I am trying to ensure is that the functions that I am going to allow, in my integrable class of functions are essentially dependent on some product type of transformation on the Brownian motion itself. So the eventual constituent of these functions will be the Brownian motion itself, evaluated at particular points. And these transformations will be bounded and continuous. So that gives me enough leverage to come up with a consistent integration theory. Quick examples. I want them to be ft adapted. So if I take an example of f1, which is the function g evaluated at b t by 2, then this is ft adapted because t by 2 is happening before t. But if I take b2t in a second example, then this is not ft adapted because 2t will happen after t. So it is not ft adapted at time point t. It is not, the history is not known. So all functions of this type where tj's are less than or equal to t will be allowed. I can take large products and then take some of them. So I can make really complicated forms, but they would still be ft adapted. You can understand now that if my information is all coming from time points before or at t, then ft adaptability is automatically guaranteed. And all my f functions, whatever f functions I can consider, they can be written as a limit of this type of sums. So this is a reasonably complicated result. So we are not even going into the idea of a proof, but this is a class that is sufficiently rich to give us a meaningful integration theory and also guarantees the adaptability that we need. So that is our first piece of restriction that we can talk about. Using that, now let me define the class of admissible functions on which I can define my Ito integral. So this is the definition of this class of functions. So I take the class of functions V, which is defined over the time interval capital S to capital T. These are functions of the type ft omega from 0 infinity cross omega to R. So they are from time cross omega to the real line, real valued functions, such that one, ft omega is ft adapted, which means they are of the form here from this result above. And two, this square integral has finite expectation. The square integral having finite expectation is an important ingredient in the definition of my stochastic integral. Because when I am going to evaluate the probability distribution of the resulting integrals, I will have to essentially evaluate the mean and the variance, because they are going to be normally distributed. We now know that it's going to be normally distributed. And to keep the variance finite, I need this function, the square integral, to be finite in expectation. So these are the two restrictions. And for such functions, for functions f coming from this capital V, we will define the Ito integral, which is f dv, using our step functions. So basically our limiting process with the step functions will be finally giving us the Ito integral, or the integral of this form, where my functions that I allow are coming from this class. So this is the class of admissible functions. I started out with elementary step functions, and the step functions we denote by phi t omega, which are like this summations. And we have already seen that the integral for the elementary step functions are given by this summation here. This is what we started out with. So this is my definition of the Ito integral. So now we can get back to the discussion of that consistency. So Abhinandan, Navonil, anyone? So we had that sandwiching argument on hold. So now we can talk about that, because now I have completed the definition of the integral.
Now it seems it's fine, because
Now,
we have restricted the functions.
Yes, I have restricted the functions in a, well, not me, Ito restricted the functions in a smart enough way so that the corresponding, now you can see that the sandwiching will work. I think that's where your discomfort was like.
Yes.
Yeah, and it's a very reasonable discomfort. So that's why I said that, hold on, let me finish the definition. Because this is a very important place where we are defining this stochastic integral. So once this concept is clear to us, the rest, as I said, is more mechanics. So we just try to develop formula like we did in class 12, integral of sin x, integral of cos x kind of formula. But this is the conceptual building block. All right, so shall I move on? Is this clear to all of you?
Yes, sir.
Because as I said, this is the crux of the matter. The choice of the endpoint makes a difference. We are trying to appreciate that fact through a very badly drawn picture like this one. But well, my lack of skills. But the idea is what it is. More importantly, the kind of functions that I'm going to allow, that has to be reasonably restricted. Otherwise, I will not get a consistent theory. So we have this result where the functions are essentially dependent on the Brownian motion, measurable FT adopted transformations, and we also restrict the functions to a square integrability type of condition to make the variance manageable. Using that, we have our integral theory as a limit of step function integration, and step function integration formula is exactly the summation. So this is our integration theory. Remember that we are using the left endpoint. The first mechanical result or the mechanics of integration is this lemma called Ito isometry lemma. What is the Ito isometry lemma? This gives us an explicit way of evaluating the stochastic integrals for elementary functions or step functions. As I said, the step functions are called elementary functions here in this language. So what is Ito isometry? If phi is bounded and elementary, so which is a step function and the steps are all bounded, then I look at this integral s to t phi dB. Take the expectation of the square of this integral. This is like evaluating the variance. You understand that after all, because we are only looking at normal distribution, all we need to evaluate is the mean and the variance. So the variance for the elementary Ito integral here is same as expectation of s to t phi square dt. You see, phi square dt is the usual dt integral, so we know how to evaluate it. It is still a random variable because there is omega inside here, but the integral part is the usual integral, and then we can evaluate the expectation of that. So expectation of phi square dt is the variance of this Ito integral of the elementary function. This will be very useful for us because, as I said, we are going to define the Ito integral as a limit of such elementary function integrals. So we will try to see whether the variance can also go through a corresponding limiting process. Because, as I said, we need to only evaluate the first two moments. Okay, so this we can easily prove, and the proof will be intuitively helpful because how we manipulate the Brownian motion inside the integral, that will be clear looking at the Ito isometry proof. And it's a very nice, very elementary proof. Okay, so look at these delta Bj terms. The delta Bj terms are the increment in Bj between the right endpoint and the left endpoint. My left-hand side integral here, I cut down into small pieces. What is happening? This integral is basically a summation whole square. The summations are of this type, summation Ej omega and delta Bj. So when I take the square, it will be like a sum of squares and cross products term. So it will be a double summation Ei Ej delta Bi delta Bj. Is that clear?
Yes, sir.
So these are like our usual, sample survey kind of results. If you recall, sample survey variance of estimators, we used similar kind of terms. So it's a double summation. So what are the individual terms? What do the individual terms look like? The individual terms look like Ei Ej delta Bi delta Bj. These are the individual terms. So now let me first evaluate the expectation of these individual terms. Now, of course, if my I and j are not equal, then this expectation will be 0 because then delta Bi and delta Bj will be independent. Okay, so is that okay? So the cross product terms of diagonal terms will be actually 0. And the diagonal terms will be given by exactly this, because then delta bi square, that expectation is dt, and dt is tj plus 1 minus tj. And of course, this ei and both of the ej's will give me expectation of ej square. And as I said, again, very important, the ej's are independent of the delta bj's by my choice, by my left endpoint choice. So I can actually write the expectation as a product of expectations. So ej square and delta bj square I can separate and evaluate the expectations. Delta bj square will give me this delta tj, and this is the contribution of ej square. Is this clear?
Sir, is this result only when B is Brownian motion or general for general?
So far, this is general, as long as I take the left endpoint.
When you take that expectation delta bi is 0, that uses the fact that it is a martingale, right?
Yes. So far I am not explicitly using normal distribution, but I am using some of the moment properties. So it is like doing least squares. To do the least squares, I don't need normal distribution. I need normal distribution only when I am testing hypothesis. This is the least squares part.
So for this result, you just need that B is a martingale. Other than that,
Yes. So as I said, I am using some of the properties, but it is not yet only for normal distribution kind of thing. But that will come very soon. We have to use that. So individual terms will be evaluated like this. This part is now more or less okay. So now I look at the whole expectation thing, the whole left-hand side here. The whole left-hand side will be, as I said, the double summation over all such terms. And obviously, because all the off-diagonal terms are 0 in expectation, I am left with only these diagonal terms. And now you can easily see that this summation is nothing but this expectation of phi squared dt. So if I had looked at phi squared dt integral, that would have been exactly of this summation form, and then I pass the expectation inside. So is the proof clear now? As I said, it's a very elementary kind of manipulation, but it highlights some very important properties we are using. Some very important properties that we have, adopted for ourselves, and we are using them one by one to create this structure. So is this clear? So we were proving something called Ito isometry for elementary functions. That Ito isometry essentially transforms the variance to a dt integral expectation, and the proof is as here. So once again, is this clear?
Yes, sir.
Yes, sir. Clear.
Okay. So then with that result, we can formally write the Ito integral. So the definition for an Ito integral is for any function in the nice set of functions, capital V, this integral s to t f db is given by limit n goes to infinity, integral s to t phi n t omega db. I write phi n here explicitly because I know that as I take the limit over n, my choice of phi will change. The rectangles will change their base. So where phi n is a sequence of elementary functions, of course, they are all elementary functions, sequence of them dependent on n, such that, this is the important part, such that the mean square error goes to 0 as n goes to infinity. So the mean square error property is very important. We have been assuming this from the very beginning in our capital A assumption set. If you recall our capital A set of assumptions, we also had the mean square convergence. So our choice of elementary functions must be such that the mean square error goes to 0 as n goes to infinity. Okay, so is this definition clear? And you can understand why we need mean square convergence, because eventually we are talking about normal distribution. So if I can manage the second moment, I am done. All right, so let us take a break here. I think that this is a good point to take a break. So unless you have any quick questions, we will take a break and resume after 30 minutes. So any quick questions? Okay, all right. So let me stop here. All right. So let us resume our Ito integral discussion. So any questions at this point? Now that you have had a little bit of time to think about this, the way we have defined the Ito integral. We have defined the Ito integral through the elementary functions. We have restricted the class of functions that we are going to allow. And we have just started the mechanics of Ito integration, proving this Ito isometry, which then leads to the general definition of Ito integral with mean square convergence. So any questions at this point? All right, so assuming that things are clear so far, let me continue. So with our definition of Ito integral with the mean square convergence here, we can also show quite fairly easily with some elementary manipulation that the Ito isometry result that we have proved for elementary functions will also hold for all functions in capital V. Because we can choose sequence of elementary functions with mean square going to 0, the difference in mean square going to 0 from F. So the Ito isometry result can be shown to also hold for a function F in V. And if I look at a sequence of functions Fn in V and a function, fixed function F, such that the mean square difference between Fn and F are, they all go to 0 as n goes to infinity, then the Fn integral Fn dv will also converge to F, the integral F dv. So this is again similar to the Riemann integral result, where a sequence of functions integrals can also converge to the limit of that function in that sense. So if I have the difference in mean square going to 0 between the functions, then the integrals will also converge to the corresponding F integral. Okay, so these two results I am not going to prove, but the proof is fairly mechanical now that you have understood how to manipulate the elementary functions along with mean square convergence. All right. So this is our setup. So in our setup so far, we have a definition of the integral And we have one operational result, the Ito isometry, which holds for all functions in V. And we also have a convergence result. So let us now try to evaluate very simple stochastic integrals. So this is our very first example. We start with the Brownian motion and we try to evaluate this integral bs dbs from 0 to small t. So our function is bs. And by convention, we usually take b0 to be exactly equal to 0. So at time 0, there is no uncertainty. B at time 0 is deterministic, equal to 0. Now, if I were looking at the standard Riemann integral, bs dbs or x dx, then the result would have been half bt square. This is the usual Riemann integral. But we will see that if we do the Ito integration, then the result will be slightly different. The result will be given by half bt square minus half t. So let us see. Let us try to do this by elementary calculations to understand how the underlying mechanics work. So let us consider this elementary function phi n, where phi n is defined as bj omega, because my f tj is now bj when I am in the interval tj to tj plus 1. So my phi n function is just summation bj over j. And then I look at this difference because I'm going to evaluate the integral for phi n. So I need to show that phi n and bs integrals are the same. So I show the mean square convergence. So expectation phi n bs whole square db ds, sorry, this is the Ito isometry that I'm going to use here. I will evaluate that this difference going to 0 from the definition of Ito integral. So phi n bs, this is equal to expectation over this summation, where within each interval, my phi n will be bj, the left end point, and bs will be bs. So this is the whole square ds. And if you now exchange the summation expectation, it will be easy to see that this is same as integral tj plus 1 s minus ts ds. Is this clear? Is this result clear?
Yes, sir.
Because see, bs, between bs and bj, the only common part is the part up to bj. So these pieces I add up, so it will be s minus ts. And if I do the integral and summation, now this is a deterministic integral, so as usual, so this will be summation j half tj plus 1 minus tj whole square. So this mean square difference here is evaluated to be this much. And if we take limit, if we make the partition smaller and smaller, we can show that this will actually go to 0. Okay, is that all right? That I can use the limiting argument here and show that this sum will go to 0.
Yes, sir.
So if I evaluate the integral for phi n, I will be done. Because then the integral for phi n will be same as the integral for the actual b function. So now I do that part. So BS dBs, then I take that as limit when the partitions go to 0, this integral over the elementary function. And integral over elementary functions will be summations of this type, because phi n is bj at the left hand point, and then I have delta bj. So I have to evaluate this summation inside. So how do I do that? I use this, again, a trick from our sample survey type of calculations. Let us look at delta bj square, which is bj plus 1 square minus bj square. That I can complete the square like this and write as delta bj whole square plus twice bj delta bj. So it is like rewriting a minus b whole square in a particular way. And then note that bt square is a summation of this term. So it is like a telescoping sum. Bt square is summation over j delta bj square. So every term will cancel the next term in the summation. Only bt square and b0 square will remain, but b0 square is 0. Now summation delta bj square from here, from the earlier manipulation, this is same as summation delta bj whole square plus twice summation bj delta bj. So picking up terms from here. So what do I have? I have bt square equal to, now summation delta bj whole square will be like t. So if I take the expectations here, this will be t, because this is the variance. And this twice summation bj delta bj will be in the limit same as integral bs dbs. Okay. Is that okay? So when I take the limit, I say that I can replace this summation here by t, and this is my integral. In the limit, this summation is actually this integral. Which means this integral bs dbs is half bt square minus half t. So I wanted to evaluate this integral directly. Instead, I have used a kind of completing the squares exercise to indirectly arrive at an expression for this integral after the limit. And finally, I say that establishes that integral bs dbs is equal to half bt square minus half t, where t is the terminal point here. So is this manipulation clear? This is a little bit of manipulation like in our undergraduate sample survey type of calculations using squares cross products type of terms. So I have done it explicitly. Later on, we won't have to do it explicitly. We will have formula for this, but I'm doing it explicitly just to understand how the manipulations work and also to make you familiar with those kind of manipulations. So is this result clear to all of you? This integral, this very simple integral bs dbs, I evaluate through limiting process of elementary integrals, and I am doing it indirectly, like here, completing a squares and cross product term, so that finally I get this result. Is this clear?
Yes, sir.
Can you all just check this and see that this is actually going through?
Yes, sir.
So this is fairly simple. The only thing to remember is that whenever I am taking limit over this kind of terms, I get the variance, and that variance has the order of t. That variance has the order of dt for each term. So when I sum over, I get t. So this integral is half bt square minus half t, as we claimed above. Uh, so I made that claim here that this integral will be half bt square minus half t, not equal to half bt square as in the Riemann integral. Also, you see the choice of the left endpoint played a role here. The choice of the left endpoint actually gave us independence between the product terms, and that helped in evaluation of this integral. So this plays a crucial role. If we had taken some other choice, like the midpoint as in Stratonovich, then in the same calculations here, when I try to complete the squares and cross products, I will not have independence. There will be some covariance terms. So if you look at this summation, this mechanism closely, if my phi n is not bj, but some point in between, then when I am evaluating this sum here, there will be covariance terms because there will be some dependent part, some overlap part. So there will be additional terms in the integral. Using similar kind of manipulation, we can evaluate it, but the result will not be half bt square minus half t. It will be something else. So it might be a nice exercise for you to try it out for the midpoint choice, which is the Stratonovich integral. You can just try it out. Okay. So this result illustrates two things. One is that stochastic integrals do not behave in the same way as Riemann integrals because there are extra terms. That's a mechanical part. Intuitively, why is it different? Why is this extra term coming here? This extra term is coming here because of the variance contribution of the stochastic nature of the variable. If the variable was deterministic, then I would have stopped at half bt square. This additional half t, if you look at it very closely, is essentially contributed from the variance of the increments. This t term, if you look back, this t term actually came from this summation of delta bj squares. So this is the contribution of the variance. This is the contribution of the uncertainty in the integrand. And that's why the Ito integrals have different results from Riemann integrals. And that difference can be precisely attributed to the variance of the process involved. Does it make sense?
Yes, sir.
So these are the two things. One is the mechanical difference between the two integrals, and the other part is the source of this difference. The source of this difference is in particular the variance part. If I did not have the variance, then it would have been a simple Riemann integral. And some easy corollaries. So if I look at this particular term bt square minus t, which is coming from here, I can think of it as a zero mean process because expectation of this thing will be zero. So expectation of bt square minus t being zero is important. Why? Because when I am looking at the integrand here, bs dbs, we have already seen that bs is a zero mean process. These are zero mean processes. Even after we do the integration, we now see that even after integration, it remains a zero mean process. This is an important result. So far it is just an example. So far it is just an example, but it is actually an important result that integrals retain the zero mean property here, the dB integrals. And why is that property important? Very simply put, in that case, all I need to evaluate is the variance of the process because it's normally distributed. So if it is mean zero, the only unknown parameter is the variance. Okay, so we'll talk about that more. So before that, let us summarize all these properties of Ito integrals, as in the properties of Riemann integrals. So what are the important properties? The first property, so let us consider pair of functions in capital V from 0 to capital T. So I'm taking capital S equal to 0. And I can think of subintervals in between, like 0 to S, S to U, U to T, like that. So what am I looking at? First property is, if I do the integral over two pieces, I get back the same result. So I want to evaluate S to T FDB, but if I evaluate S to U and U to T separately and then add them back, I will get a consistent result. So it doesn't matter whether I do it in pieces or I do it together. Again, for Riemann integral, this result is true. As a linear transformation result, that is also true. Integral of CF plus G is same as C integral F plus integral of G. So I have this linearity property of integrals. This is a new one because, of course, for Riemann integral, these things don't make sense. Expectation of a dB integral is 0. We have already seen it for one example, but in general, this is true. We can establish this by the usual interchange argument. And here the interchange argument will work because we have the finite square integral expectation property. Remember, in capital V, we had integral f square expectation to be finite, and hence the interchange of summation expectation is valid here. Is this known to you? Because typically these are taught in probability courses. Is this result known? Class, can you confirm that what I just said is known to you? Can you hear me? Hello?
Yes, sir.
So is this result known to you? Because I think these results are taught in probability courses, but I just want to confirm. This interchange of summation and expectation operation. So what I am using here is that we restricted the functions, admissible functions in capital V with this property. The expectation of square integral is finite. So we started out with this restriction, and now I am saying that to establish the zero mean property of the integral, I can use that restriction and interchange the summation and expectation inside. Summation as in for elementary functions, and then I will take the limit. So is this clear? Is this result known? So is this not known? So can someone clarify? Because I thought this would be okay. Sushmit, can you confirm whether this is known?
Sir, I mean the third point, that expectation of integral is 0.
Yes. No, see, that property is something that we are discussing now, but to prove that the operation that we need is the interchange of summation and expectation. And I say that the validity of this interchange, this exchange of summation and expectation, is taught in the probability courses typically, in the limit theorem type of probability course. So have you done that? I can't recall the
No, I
exact
guess.
names, but sorry. Yes.
I think no. I think we aren't taught that.
You have not been taught any kind of convergence theorems, MCT, DCT, this kind of results.
Yeah. Yes.
So in DCT, what did you do can you recall in the dominated convergence theorem?
So the main point was to whether the limit of integral can be written as integral of limits.
Yes.
And that can be used to find out whether the limit of expectation xn is equal to expectation of the limiting random variable or not.
Right. So now can you see that I am using the same thing here?
Okay, sir. Okay, sir. Okay, sir.
So once again, to the whole class, this is like the dominated convergence theorem that you must have learned earlier. The notations may be slightly different because I am talking about integration, and there you talked about expectation, but these two are same things really. And I am using similar logic, similar properties. So if the connection is not immediately apparent, just go back to your probability textbook after the class and check. This is not unknown to you, I am sure. Only that you may have forgotten, or maybe the difference in the notation and context is confusing you a little bit. But in essence, this result is known, and using that exchange result, I am saying that this will hold, that expectation of dB type integrals will be 0. And the fourth property now is quite expected, that this integrals f dB from capital S to capital T will be f capital T adapted. This will be true because you already know what are the class, actually what is the representation of this class of functions in capital V. The representation of these functions are essentially product of transformation on Brownian motions and then their sums. So whatever I do, if you go back to that, so let me go back to that result. So this is the result I am talking about. Whatever we do, the functions in capital V are essentially of this form: product, then sum over them. And these are all by construction FT adapted. And then I do integration. And of course, integration is like a summation with elementary functions, and then you take the limit. Sorry, integration is like summation, and then you take the limit. So when you take the summation, you can show that they will remain FT adapted, and then you take the limit and show that this carries over because of the mean square convergence here. So again, I am not giving you formal proofs. I am just talking about what are the steps that are involved. But these steps are actually known. We have used them, learned them earlier, but we are now using them in a different context. So both for property 3 and property 4, I'm using properties which are already discussed earlier. 3 is like our convergence theorem result, and 4 is actually using the characterization of all the functions in capital V. And using that, and using the usual elementary function argument, one can show that the integral, which is nothing but a limiting sum, that is also FT adapted. So if I start with FT adapted functions, and then I take integration, I do integration, Ito integration, the result I get is again FT adapted. This will be very important for our financial applications because we want to go back to financial applications with this, because for us, whenever we are creating portfolios and doing investment decisions, FT adaptedness is crucial because we can only use information up to the current time. So this Ito integral property being FT adapted and being mean zero will be extremely critical when we go back to finance and use these results for our financial theory. Okay, so that is the Ito integral properties. Now let me redefine martingale. We have defined martingale earlier for our discrete setup in the first half of the course. Now let me rewrite my definition for the continuous time processes. So I say that a stochastic process MT on omega strict F and P is a martingale, will be called a martingale if the absolute expectation is finite for all T. That is one important restriction. Earlier, we didn't have to write it explicitly because of the finite domain, but now it has to be written explicitly. And of course, the martingale property that given information up to T, if I compute conditional expectation of MS given MT, it will be equal to MT. So the conditional expectation is equal to the latest available value. So if I am conditioning on information up to T, then expectation of MS will be MT. That's the usual martingale property. And of course, the absolute expectation finiteness is now crucial. So martingales, again, we have come across martingales in our financial discussion. So we want the martingale property to play out and see what happens with the stochastic integrals. So important result, an Ito integral is a martingale. And again, the proof is fairly straightforward, but again, I will just go through these steps quickly because it's not the mechanics, but the conceptual clarity that will be very important for us. So an Ito integral is like this FdB, and what I want to show is essentially the conditional expectation property, because we have already shown the square integrable property. So by Cauchy-Schwarz inequality, the absolute expectation will be finite. That we already know. Because the square expectation is finite, absolute expectation will be also finite. Okay? So the first part is correct for an Ito integral?
Yes, sir.
Yeah. So the second part, this conditional expectation part, is now easy. Now it is more mechanical. So what I will do is, so S is some point to the right of T. So I have this integral 0 to S, and I have information up to 0 to T. So conditional expectation. So I'll just split the integral in two parts. 0 up to capital T, this will be capital T, and then capital T to capital S. This part is already known, so it will stay as it is. How about this part? We know that property 3, Ito integrals have mean 0, expectation 0. So the new part, which is unknown, will have expectation 0. So the conditional expectation of the whole integral given up to some part will be same as the latest available information. All right. So this is very straightforward. You could have done it very easily yourself, but I'm just emphasizing what are the properties that are being used in these steps. because a little bit of care is required. Okay, so we have very nice properties for the Ito integral. We have the linearity property, we have this interval splitting property, we have mean zero property, and FT adaptedness. Not only that, we have much more. We also now know that Ito integrals are martingales. So that gives us a lot of structure on the Ito integral. So if we are going to use it in the financial math problems, which we are going to do, we will be in very good shape, because a lot of properties that we have been discussing in the discrete setup earlier, we have been able to establish in this continuous setup in a much more abstract setting, which will be useful for us. Okay. A simple corollary is that a Brownian motion is a martingale, because we can actually show that the Brownian motion can be written as a summation. So it is like an integral. So integrals are martingales, so Brownian motion is a martingale. And then a second property comes from the first part. We can also show that, take this Ito integral, f dB, I can always find a continuous version of this Ito integral. So in effect, I can always assume that the Ito integral is continuous in T. So that continuous path properties that we have defined earlier now is inherited by the Ito integral. So the Ito integral is a martingale and it has the continuous path properties. So is this clear? So again, we have talked about a few of the very important properties. So I just want to make sure that you are with me, like you understand what are these properties really. Not only that, also they have important implications in our financial modeling later on. So are these results clear? So I have all this linearity, zero expectation properties. Then I have the martingale property and I have the continuous path property. So is it okay?
Yes, sir.
So in effect, then what we have is we can summarize all this in a theorem that if I have a function f from capital V, then integral f dB has a T continuous version. So I can choose a continuous version of that, and the integral will be a martingale. So it will be a martingale and it will have continuous paths. Okay, now just for the sake of completeness, I'm just going to show you an extension of the Ito integral. We will not be using it explicitly, but sometimes in financial modeling, we have to handle more than one dimensions at the same time, maybe two sources of uncertainty. In those cases, we have a multidimensional setup, and then an extension of the Ito integral to a multidimensional setup would be important for us. It, mechanically speaking, it can be done very straightforward manner, but of course the notation is going to be clumsy. So let me just outline the idea to you, but we are not going to use it a lot. So what I am talking about is, let us say B is a n-dimensional Brownian motion. So it's like a multivariate normal distribution, B1, B2, Bn. Capital V m cross n are matrix functions. So all the matrices Vij, T, omega. So each element is a function from capital V earlier. So I create a matrix out of that. And now I can define a multidimensional integral like this, S to T V dV, which would be in full like this in terms of term-wise integrals. Term-wise, it will be like the matrix into vector multiplication, and then I can define the integral inside as I have done before for the single dimension. So a multidimensional version can be created from this one-dimensional Ito integral theory. We are not going to use it a lot, but in a few cases in financial modeling that we will see, we will have to handle more than one source of uncertainty at the same time. And then a two-dimensional model sometimes will have to be used. And that's why I thought that we need to mention this here. Okay, so for the time being, let's just keep it at the back of our mind because we are not going to use it directly. But if necessary, we can always extend Ito integrals to more than one dimension. For now, these other properties, martingale and continuous path, these will be more important for us. Okay, so let me actually stop here because I don't want to get on to the next topic right now because it will take us in a different direction. So let me stop here for today and take questions. If you have questions, you can ask me. Otherwise, we'll resume on Wednesday. So are there any clarifications or quick doubts that you want to clear?
Sir.
Yes.
Sir, I have doubt regarding the assignment. So,
regarding the assignment, yes.
So there is a section that we have to write the types of modeling of the contracts. So
write the types of. Can you repeat?
Like how can we model the contracts?
How can we model the contracts? Yes. Okay.
Yeah. So there, what should what should we write? Because for option pricing there is binomial model. So should we write that particular thing, or there will be something special to that particular commodity? And if it is so, then from where that we can get that information?
Well, I thought that is the assignment. You are supposed to search the literature for that. You see, for the specific commodity that you have been given, everybody has been given a different commodity. Yeah. They have certain physical properties. And because of those physical properties, some particular type of modeling may be relevant for them. That's what you are supposed to find out. I am not asking you to develop a new model. All I am asking you is to find out what are the appropriate models that are used in the literature. You have access to a lot of electronic.
That was my question. Like, can we implement the models that are already given in the book, or we have to make some new model? That was my question.
First of all, you don't have to implement anything. This is a reading assignment. You are not going to implement.
Yeah.
And secondly, no, this is not a new model development exercise because that is a much more difficult exercise. This is a review of existing models and why those models are appropriate. As I said, because of the physical characteristics of the item, certain models are appropriate. There should be a logical connection. That logical connection you have to find from the literature and summarize in your own words. That's the job.
Okay.
Any questions related to today's class? Whatever we have done today? Okay, so if there are no questions as of now, we will stop for the day, and we'll resume on Wednesday. And in the classroom Dropbox, I have shared a biodata of the speaker for the 16th November class, the blockchain in finance, along with a Google Drive link. Just check whether you can access the material there. I don't know whether it's email specific, so I have just shared the link. If it works, let me know. If it doesn't, also let me know, because then I'll have to ask the speaker to send it in a more friendly way. Okay.